In this video, I'm going to go over a few examples in which I'll be classifying an ordinary differential equation. And I'll be classifying it by order and also by linearity, whether it's linear or not. So these instructions that I've written here are the instructions for all of the 3 examples I have for you in this video. So first I'm going to state the order of the ordinary differential equation, and then I'm going to determine whether the equation is considered linear or non-linear. Alright, so the first equation I'm looking at, the quantity 1 minus x times the second derivative of y, where here it would then be assumed that y is a function of x, and I'll write out what's the dependent variable and independent variables in a second. But that's y double prime minus 4 times x times y prime plus 5y equals the cosine of x. Right. So as I mentioned, the variables here that show up in this equation, because we have our derivatives and whatnot on the y's, that'll be our dependent variable. Right, dependent variable is y. And the other variables that show up here are just x. So we're going to be in this equation here, we're assuming that y is dependent on x. So x is our independent variable. Right, and when you see the y prime or the y double prime, remember in Leibniz notation, another way to write that would be dy dx, right? It's derivative of y with respect to x. And y double prime you could also write this way as d2y over dx2, right, like that. And you could also use dot notation. Like there's other notations that you're going to see in differential equations. Okay, so first we're going to classify by order. Okay, now the order of a differential equation is simply the highest order derivative of the dependent variable you're seeing. So I'm just going to write highest derivative that you see. All right, so for this example, y is the dependent variable. You're seeing the first derivative of y with respect to x. And here I'm seeing the second derivative of y with respect to x, y double prime. And that's the largest, the highest order derivative I'm seeing. So this is a second order equation. Alright, so that's part 1. Right, state the order of this equation. Alright, now the next part might be a little trickier. We're going to classify this based on linearity. So is it linear or not? Now what I'm going to write here is basically the general form. If y is the dependent variable and x is the independent variable, now these don't always have to be the dependent and independent variables. You may see in other problems the dependent variable is y and the independent variable is t, or the dependent variable is x and the independent variable is t or y or whatever, right? These don't have to be y and x all the time, but for our purposes, for our examples, it'll be either y and x or y and t. Right? So again, if the dependent variable is y and the independent variable is x, an nth order linear equation, right, linear differential equation, will can take the following form. We have a sub n of x multiplied by, the nth derivative of y, right? Well, y with a little parentheses around n, because it's not y to the nth power, it's the nth derivative, plus, and then a sub, n minus 1 of x times the n minus first derivative, and this would go on like this, all the way down to, a sub 1 of x times y, the first derivative, y prime, plus a sub 0 of x times y, right, the 0th derivative, or just y itself, equals, and then some say some function g of x. Right. So a nth order linear equation, can take on this form. Now notice here that all the derivatives, they would say, are linear or first degree, because you have the every single derivative, the nth derivative, the n minus first derivative, the first derivative, the function itself, y, they're all to the first power. Right, so you're not going to see the first derivative squared or the second derivative cubed. Right, all the derivatives are to the first power, and all the coefficients, right, this a sub n of x, a sub n minus 1 of x, a sub 1 of x, a sub 0 of x, the g of x on the other side, all the coefficients depend on, at most, the independent variable, just x. Notice that none of these coefficients, none of these functions depend on y. Right? And if they did, if any one of these did depend on y as well, the dependent variable, then it would not be considered linear. Right? So looking back at this equation here, this second order equation, it's got this kind of form, right? You have a function of just x times the second derivative to the first power, plus another function of just x, right, negative 4x times the first derivative to the first power, plus, and then a function that depends on at most x, just 5 constant, times the function y to the first power, equals, and then over here a function of just x, a function of at most x, but not y. So this does take on this linear form. Right, this is also a linear equation. So all total, this is a second order linear equation. A second order linear differential equation, and usually I'll just put DE, capital DE, for differential equation. And for ordinary differential equations, you may see them put the O in front of it, ordinary differential equations. Okay, so that's the first example. Took a little longer than the other two are, because I went through and explained everything what I was looking for. So let's take a look at another one. Right. So here's another one where the dependent variable is again y. Right, y is a function of, this time, t. It's assumed that the independent variable here is t, which could be like time or something. So I'm saying t to the fifth, times the fourth derivative of y, and that fourth derivative of y is, to the first power. Right. Minus t cubed times the second derivative of y with respect to t. Right, this would be like d2y over dt2, right, dt squared. But this second derivative is to the first power, right, plus 6 times y to the, this is the 0th derivative, right, the function itself. And then we have equals 0 on the other side. So first off, the order, really easy, right? The largest derivative of the dependent variable I'm seeing is the fourth derivative. So this is a fourth order differential equation, right? And then the question is, again, is it linear or not? Well, look at all the derivatives. They are to the first power, right? Y to the first, y to the second. The second derivative is to the first power. The fourth derivative is to the first power. And all the coefficients, right, all the coefficients of these derivatives are functions of at most t. Right, you don't have, this is t to the fifth, and that's it. It's a function of t times the fourth derivative here. Now if I had another y here, right, if this was y times t to the fifth, times the fourth derivative of y, then it wouldn't be linear. Okay, all the coefficients would have to be a function of at most the independent variable, t. So t to the fifth, great. Negative t cubed, awesome. Positive 6, wonderful. And then 0, excellent. All right, every single coefficient is a function of at most t. So this equation is a fourth order linear differential equation. Great, simple as that. All right, now it's got one more example here. Obviously you'll see a bunch if you're practicing a lot. This isn't going to cover every single possible example you'll come across, but here's one last one. All right, still an ordinary differential equation. So on the left side here, I've got the second derivative of y with respect to x, which again I could call y double prime. Right. And over here I have the square root of 1 plus, and then the first derivative of y with respect to x, but then that's squared. And you could write it this way as well. These are the same equation. So y double prime equals the square root of 1 plus y prime squared. Now right away I can see it's a second order equation. Right? The highest derivative of the dependent variable, the dependent function, is the second derivative. So this is a second order equation. Oops, can't spell order. There's a D in there, sorry. Now I'll just scratch that off and put the word order properly. Okay, so it's a second order equation, but it's not linear, right? Because this term here. See, I have a derivative that's raised to a power other than 1. It's the first derivative squared. So because of that term there, this is a second order non-linear differential equation. Right. Okay, second order non-linear. Now, you could also have said, I don't like the square root, and squared both sides, but even then you would see that it's non-linear, right? Because if I got rid of that square root, I'd end up with y double prime squared equals 1 plus y prime squared, and either way you have a derivative or derivatives, right, that are not raised to the first power, right? So it's a second order non-linear differential equation. I guess I could throw out one more example here, like going back here. If I wanted to say, hey, let's make this non-linear, there's a lot of things that could make it non-linear. What if instead of 0 over here, I had the sine of y plus t, or something like that. Well, now all my coefficients, the t to the fifth is fine, the negative t cubed is fine, the positive 6 is fine. This coefficient over here, the sine of y plus t, depends on not just the independent variable, right? It depends on the dependent variable. So because of this sine of y plus t, it would be a non-linear equation All right, still fit fourth order, all right, but non-linear because of the sign of y plus t there. All right, so again, just I can't possibly throw out every possible example you're going to see. Just I'm hoping, looking at all these, you can very easily look at an ordinary differential equation and state the order, and then also state whether or not it's linear. And thanks for watching.